Hello and welcome. This is the second video I am recording today, and this video will be regarding separation processes, part B of homework 3. And to do that, um, sorry, I lost my train of thought. To do that, there are going to be three things in this part B, and I will kind of read the problem assignment to you. The first is going to be derive an expression from the boil-up ratio in terms of liquid fraction of feed and reflux ratio, which we mentioned in the first portion of this homework. And we will derive an expression for determining that equilibrium liquid composition, giving the vapor fraction of a more volatile component in a binary mixture for fixed relative volatility. Every time I read these descriptions, it sounds so terrible, but I promise it's not as bad as it sounds. The second part, we're going to write code to automate the generation of a McCabe-Thiele diagram for constant relative volatility and a total condenser. So we're going to do some work in Colab today, as we have done in most videos. And we're going to demonstrate that code for relative volatilities of 2 and 5, and then at a decreasing reflux ratios from 100 to at 2, at 1.5, 1. And we're going to explain the observations that we see in each one. And then finally, for an existing operating column with a fixed number of stages, we're going to describe what actually happens as the reflux ratio is reduced, as we mentioned in part 2, and what needs to be iterated on that McCabe-Thiele analysis to reflect that. So a lot of mumbo jumbo just came out of my mouth. If it does not make sense yet, that is perfectly fine. It doesn't even necessarily make sense to me yet. I am learning with you guys as I make these videos, so stick with me here and we will work through this step by step. So as you can see, I have this diagram written on the left. We have a feed going in. I'll use this. We have a feed going in. We have a V bar also going in, and then we have our V leaving. And so the first thing we're going to do is create an equation. That's usually our first step always. And so to do this, over here we have 1 minus Q times our feed value plus V bar is going to be equal to V. And so the reason there was a part A to this homework is to give us kind of the backbone and the background for what we're doing here. And so what I want to do here is recall this equation, this that I have above. And so what we're going to actually do is just copy this down. Oh, that's not what we want. Shoot. So I'm going to copy. Okay. We're going to bring this down here. Paste it here. We're going to make it rather small. And so, as I said, we have our vapor coming up, our liquid coming back in, and our distillate leaving, which will be very important in this portion of the homework. And now from these diagrams, we're going to get a couple more equations. So, if you guys recall, one of our major equations we used previously was our reflux, which is going to be equal to liquid over distillate. Then we also have our V is going to be equal liquid plus distillate. And from here, kind of combining both of those equations, we're going to arrive at a generalized equation that is distillate times our reflux plus 1 is going to be equal to R1 minus Q times our feed. And then from here, we're going to add that V bar. So again, it's kind of a similar process. We draw our figure, we take that figure, we create equations, and then we kind of combine those equations to help us reach our ultimate goal, which is this equation. Not our ultimate goal, a necessary stepping stone to reach our goal, which is this equation. And so now the next portion of this is we're going to be using this equation, rearranging it to find our boil-up ratio. And so to do this, we're going to first isolate V bar by itself, in which you get V bar is equal to D times R plus 1 minus 1 minus Q times feed. And then again, we used this in our previous equation. The ratio V boil up is equal to the ratio of V bar over our boil up. And when you substitute that into the equation, you're going to arrive at that boil up ratio. So I will write this off to the right side. And that is going to be VB, or boil up, is equal to our distillate times the reflux plus 1, subtracting our feed times 1 minus Q, that all divided by our boil up ratio, or our boilet, why am I, what word is it? Boilant, sorry. And so this I will square off, This is our boil up ratio. So now we've completed that first portion of part one of part B. So now we actually need to derive an expression for
We have
determining.
y underscore.
So to do this, we're going to start working with the variable alpha. There's going to be a lot of algebra in these next few steps. So I will do my best not to make any mistakes. So at first we know that our alpha is going to just be originally the ratio of our y1 to our x1, which can also be written as y2 minus x2, which it's just a continuous step by step. y1, y minus y1, or 1 minus x1. Now from here we can kind of combine like terms, and we will say that alpha is going to be equal to y1 times 1 minus x1 times x1, 1 minus y1. And then from here again, you can cross multiply to get alpha x1 minus alpha x1 y1 is equal to y1 minus x1 y1. So now that we have all of this alpha in our algebraic equations, we're going to want to separate x1 and y1 onto different sides. And to get that, you will arrive at x1 is going to be multiplied by alpha minus alpha y1 plus y1, and that's going to be equal to y1. And then divide by this here, you get x1 is equal to y1 divided by alpha, y1 plus alpha times 1 minus y1. And this here, which I will box off, is our second equation, or the answer to the second part. This is the actual expression for determining the equilibrium liquid composition given the vapor fraction. And so from here we will use these two green equations and we will go into Colab. So as you can see, I moved into Colab and I'm going to first run our library in just to get all of the necessary, sorry, my brain keeps freezing, all the necessary information into Colab. Let that run for a second. Once we get the green check, we will continue writing our code. Usually it's 11 seconds. Let's see if I'm right. 10, 11. Oh, I'm good. All right, so the first thing that we're going to want to do is input our values. So let's add a line of code. The first one is going to be our alpha value, which is going to be equal to 3 per our specs. And then we're going to define our x equilibrium function, which we will label as f function of y. And this is going to return a value of y divided by y plus alpha, which we made 3, times 1 minus y. And you could be asking, well, where are you getting all these equations? All these equations are going to be what we derived on the iPad previously. That's where we're getting all of this. So next, we would need our y equation. We want to get out of this. We're going to say y eq, and that is going to be equal to np dot lit space, and we want 0, 1, and 51. Then we also need our x equation, which we'll label as x eq is equal to x underscore equilibrium function, and that is going to be a function of now y eq. Let's run this to make sure everything is good. Good. Now, we will be adding another line of code, and now we will be kind of defining a lot of our variables. And so the first one is going to be f, which is our feed, and our feed is going to be 1 mole per second. So we will label that mole per second. And then we also need our zf variable that we got, which is 0.4. We need our q, 0.9, and this is going to be the fraction liquid in feed. And again, all as you notice, all these variables that we are using are the ones that we used in our derivation equations. And now RD is going to be equal to 0.95. XD, which is our distillate, is going to be 0.980. And then our reflux is going to be a value of 2. Now, the equation for all this, the distillate is going to be equal to our RD times our feed times our Z F value all divided by our X distillate. Enter. And then our boilant is going to be equal to our feed minus our distillate, obviously, because remember that dotted cage we kind of drew around. We had our feed going in, we had our distillate coming out, and our boilant coming out. So obviously if our feed is equal to our boilant and our distillate, that's how you arrive at that equation. Now we have the composition times our boilant, and that is going to be equal to our CF value times F minus our composition of our distillate times our distillate. And this will all be divided by our boilant. We also need our vapor boilant, and that is going to be equal to our distillate times our reflux ratio plus 1, which will then also be subtracted from 1 minus Q, and that Q value will be multiplied by our feed stream. And again, all of this will be divided by B. And then again, just a reminder, this is the boil up ratio that we solve for in the last part of what I did on the iPad. And so now we have our X RS and our Y RS. And so here we're going to have X boil up divided by our vapor sub B. And this will be added to concentration of our distillate divided by the reflux plus 1. That will all be divided by VB plus 1 divided by VB. VB is bar, by the way. I think, I don't know if I said that previously, just so we are aware. And that. And then this is going to be equal to our reflux divided by reflux plus 1. We have one too many parentheses here. Times X underscore RS, which is the equation above. We're going to add that to our XD divided by reflux plus 1. Now let's get rid of this. Let's run this, make sure everything's okay. We do have an error. VB underscore 1. Where do I have that? Where did I write VB underscore 1? Oh, sorry, this is meant to be plus 1. Run it, and we are good to continue to the next portion. So the next portion is just going to be some more variable definitions. So this next portion is going to be actually our step function that is going to show you how many levels you need to achieve a certain required value, or desired, sorry. And so here we want to set our n max equal to 50. And as I said, this is going to be related to our steps. And we want our steps to be equal to, oh, this is bad typing, XD, XD. And in this one, our Y equilibrium is going to be equal to XD. Now we're going to make a for loop for I in range. Again, this is why it's a step function. It's going to be taking a value for every value that we desire. And now for our x equilibrium, we want this to equal our x equilibrium function. And we want this to be a function of y underscore equilibrium. Keep making typing errors. X equal, okay. And now next we want our steps to kind of create this append is just going to be making a list, and that is exactly what we need. But we don't need the second part. We want the x equal, y equal, but we want to create an if statement in this for loop, which will be if our x equilibrium is less than our concentration of the boilant, we want to break. Get out of the if loop, and then we want y underscore, and this is going to be equal to our reflux times our x underscore equilibrium function. And we want to make that function of, oh, sorry, I was retyping out what I already done. My brain, I keep having brain farts. Oh well, this is going to be our reflux times our x equilibrium divided by our reflux plus 1, and this is all going to be added to the concentration of our distillate divided by the reflux plus 1. Now we need the stripping section, which is going to be y equal underscore strip, and I'll just type all these out so you guys understand what we are going to be saying. And then we also need our y underscore equilibrium. And so the stripping section is going to be what we actually derived, which is v bar plus 1 multiplied by x equilibrium divided by v bar. And this is going to, and then we're going to subtract away concentration of boilant divided by v bar. And then here we want the minimum value from our y rectifying and our y stripping. I hope it's kind of coming together why we did what we did in the first part of this. And then we want xy steps, and we want to append the current library, which will then be x equal, comma, y equal. So the next portion of this is what we want to return. So we want to get all the way out of this. And we want to say xy steps, which is going to be our step function, is going to be an array of all of the values. So it's keeping track of all of them. So let's run this, make sure it's good. And it is good, and we were able to continue. So now we're on to the final portion in which we're going to be plotting all of these very intricate lines. So we're going to do fig equals make underscore subplots. And now we're going to create roughly, I think it's like 6, maybe 7 scatter plots. And so we're going to make this simpler on ourselves. We're going to do fig dot add underscore scatter. And we're going to get rid of this. We're going to copy this. And like I said, I believe it's, I think it's 6. Okay, and then the last part will be fig dot update underscore layout. Okay, so now the first one is going to be, they're all going to be, let me see, think how I want to say this. So the X is going to be more towards the concentrations, whereas the Y is going to be everything in terms of our reflux. It'll make more sense once you are actually able to see these scatter plots. So it's going to be a minute. I'm going to have to type out all of these. So we want X, D, and 0. And then we want Y to be equal to XD divided by, this is, like I said, the reflux is going to be incorporated here. And then we want mode. Oh, why did you do that? You want the mode to be equal to lines. Now here, x is going to be, oh, let's close this off. X is going to be equal to, now our boilant, so we have our distillate at the top, now we're doing our boilant. And now we want our V bar plus XB. And this, go out of this parentheses, this is going to be divided by V bar plus 1. Forgot to add a parenthesis there. And then Y is going to be equal to XB 1 mode equals lines. Now this one, X is going to equal X underscore RS and ZF. Close that bracket. Y is going to be equal to another bracket, Y underscore RS and ZF. Mode here, again, lines. You know what, let's just copy this. And so at the end of every single one, we are able to, that was wrong. So at the end, we can just start copying and pasting this. So now the fourth one is going to where we incorporate our steps. And that is actually exactly what we need. So we're going to do that, but we don't want this. We want lines, not markers. And then here we are going to do our X equilibrium. And our Y is going to be equal to our Y equilibrium. Mode lines, thank you. And then the last portion is going to be our steps. And we want that to be 1, 0, and 1. Mode lines, that is what we want, but then we also want a portion of line underscore color. And that is going to be equal to, let's make it blue. No, we'll do gray. And then we want to update this. We want our width to be equal to 500. Height equal to 500. And show legend equals false. So now we are going to print this. See what we make. Error. All right, I'm going to fix this and come back. So now, before we continue, I want to explain what we have here. So we have our stripping line here in red and our rectifying line right here in blue. And then this gray line is our, shoot, I forgot, one second. So I forgot the word. So this is our operating line, rectifying line, and then our, as I mentioned before, what's not rectifying? There's rectifying, and then there was stripping. Sorry. So stripping, rectifying, operating line. And this purple line is our step functions that shows you how many steps would be needed to be completed to actually get to that equilibrium point, which is this green, which is where the stripping and the rectifying actually intersect. And now we are able to move on to the problem statement in which we slowly decrease our step functions. And so now what we're actually going to want to do is see what happens to these steps first when we change this alpha value. So if we change this alpha value to 2, let's see what happens. Okay, so this is exactly what we're looking for. You can see these step functions. I'll zoom in a little bit, they are not going to go past this orange rectifying line. because that's just not possible. So these steps will get smaller and smaller and smaller, and then once it hits this intersection, it's not going to go past that. So now that we've switched that to 2, we're going to look at our reflux ratio, which again is that ratio of liquid. Sorry, I keep liquid to distillate. And so let's make this super, super large, and let's see what happens. Like we said, 1,000. And as you can see, that has actually allowed our rectifying line and our stripping line to become parallel with this operating line because it is such a large ratio of liquid to distillate. Now, if we were to drop this down to 5, let's see what happens. As you can see, this is kind of what we had at the beginning. These steps continue all the way till the intersection. And now what happens if we drop this down to 2? There we go, back to this, which we've seen before. Let's do 1.5. And as you can see, the ratio, as we get a smaller and smaller ratio of liquid to distillate, these steps are going to become smaller and smaller and smaller and smaller. So let's see what happens at 1. Even smaller. Finally, let's do 0.5. So the conclusion we can make from this is that as you continuously increase the ratio, there's going to be more and more steps needed to reach a desired value. And when you shrink that ratio down, these steps are going to get smaller and smaller and smaller because they're unable to pass this rectifying line here in blue. So now, as I explained, we'll kind of review all of what we have done. Here, I will bring... Actually, going to bring my iPad back into this. As we mentioned, we found these first 2 equations that allowed us to code this in Colab. And from here, let me, excuse me, I have the hiccups, center this back up. From here, we were able to actually adjust this ratio. And as the ratio becomes smaller and smaller, you're getting closer to that equilibrium line, which is going to make it harder and harder to create steps. So I appreciate you following along with me. As a reminder, today we drove an expression for the boil-up ratio and then actually found an expression to determine that equilibrium liquid composition. And then from here we were able to make a code for the McCabe-Thiele diagram with a decreasing reflux ratio. And then we also, for an existing column, we were able to have a fixed number of stages and describe what happens when the reflux ratio is reduced. So thank you for watching.